Okay. So, there are several things I wanted to talk about, one of which is, I suppose the first topic is EMF. Symbol for that is a script E, and this is, of course, it stands for electromotive force. It turns out it's not really force at all. If anything, it is sort of like work done per unit charge or something like that. So it's a potential. Yeah, it's an EMF. It's a potential. It's like the voltage of a battery. So the source, one way to, let me consider the simplest case, and then I'll mention more general case. So imagine you just take a battery and no wire is a conductor, so even if you don't add a resistor to it, this wire itself will have some amount of, no wire is a perfect conductor is what I mean. There's some amount of resistance in it. So to make that explicitly clear, I'll just throw a resistor in there. I'll call these points A and B. As a result, there will be an electric field in this direction. There's a current in this direction. And if you use an ohmic material, J is sigma E, so there it is, there's the current. But when you go back around, all the way here, the potential difference must be 0. If you go along the electric field, the potential is decreasing. Yeah? So that means over here, it has to decrease as well. It should be path independent. So inside the battery, if you will, the electric field is pointing the other direction. Otherwise, you won't get E dot dl to be 0. Okay? But in the battery, there's also a source. Something that pushes charge from one side to the other, and I will denote this as F of S. But it's script F. What does that mean? It means it's force per unit charge. So in general, F is equal to F of S. Well, E is also force per unit charge. Yeah? Now, in this case, this is a battery. Otherwise, it could be some other external electric field or magnetic field or something. So the definition of EMF is at any instant of time. You freeze an instant of time, and then you do F dot dl. It is not really the work of anything, so to speak. It is a frozen F dot dl. Okay. Well, that can be written as, but what does this got to do with typically a battery? Well, E dot dl through a closed loop is what? 0. So EMF now reduces to just this guy. But this is only non-zero inside the battery. So this is not your typical definition of EMF that you've seen in freshman physics, but then again, our approach has been rather general at every stage. Now, for a perfect battery, F of S is equal to the net force, just force per unit, just cancels out. Yeah? So in that case, EMF is equal to E dot dl and you can see that this is nothing more than the potential difference of the battery. In freshman physics, this is what we were just saying. It's the voltage in the battery. If you look at a 1.5 volt battery, the EMF is 1.5. That doesn't really mean, this potential has to be distinguished actually from terminal voltage, because every battery has an internal resistance. Yeah? So if you take a 1.5 volt battery and you connect it to a load and use a multimeter, you won't see 1.5, you'll see slightly less. But the point you have to remember is we have connected this to an EMF, but the point you have to remember is the fact that the most general expression is the net forces on the charges in a circuit. That is what EMF is. In this case, the EMF was provided by the battery. It's very abstract. We haven't done anything with it. We will. In fact, let's do a problem very quickly. I was thinking I should do it later, but sooner is always better. This is example 7.4. It's hard to draw. So you have a spinning disk that can spin about a central axis, and it's spinning. It's a conducting disk. It has some radius r. And the disk is spinning in an external uniform magnetic field B. And then you connect the center of the disk and this terminal, this end, and you want to know what, and maybe connected to some sort of a resistor. You want to know what's the EMF, what's the voltage. So if you can spin a conducting surface in the magnetic plane, you can generate currents. Well, let's see why is that the case. So you look at, so let's look at this spinning thing head on, huh? It's not the center. And let's consider some point over here. And I'm going to use cylindrical coordinate system. This distance is S. There's a speed that is tangential to a circular path, V, and in magnitude, it's omega cross R, but in magnitude, it is S omega. The B field is coming out of the board in this diagram, because we're looking at it top down. So this is B. What is the force per unit charge? It's V cross B, but what's the direction? It is V cross B, so it is S omega B, V tangential, B coming out of the board. Cylindrical coordinate system. What is the direction? Very good. It's that way. That's fine, because we really want charges to suffer a magnetic force outward. And that's how the EMF is created. S hat. So then, this is the expression I'm going to use. dl equals ds s hat. So EMF is, it's a closed loop, but there's no magnetic force on this part. Well, we're giving it sufficiently away. And we'll get F dot dl from 0 to r, and that is S B S hat dot ds s hat 0 to r. So that is omega b s ds, that's s squared over 2. Well, we can just integrate it. And that is the current you get. Make sure that, yeah, I think the book used A instead of R. So just by having a rotating conducting disk, we'll see something similar. I should ask Dr. Ajaz if I have the setup. If we do, I can bring it to class. It's easy enough to get a spinning conducting disk. Relatively easy to get a uniform magnetic field. You get an EMF. It's kind of neat. Yeah. Okay. So this will be a constant feature for a while. You move in a magnetic field, you generate a EMF. And what's even better, there'll be a beautiful geometric description of this EMF. So what we're going to do now is exactly what I just mentioned, motional EMF. Well, I think that's just the title. It's not a grand old title. It's just somewhat descriptive. So what we have is a uniform magnetic field in a certain region, in this much region. So there is magnetic field into the board. Okay? And then you have a loop. The loop extends a little bit to the outside. Well, all loops have resistors. It's a rigid loop. So, you know, maybe you have a plastic frame and the wire just loops along the plastic frame, so it is rigid. And then you pull on it. You pull on it with the speed V. The question is, what happens? So there is V over here. The positive charges, of course, the negative charges are the charges that are actually moving. Electrons are moving, but we'll we'll draw it as positive current in this direction. It actually means electrons are going in the other direction. That's just a habit. So this is V, that's B, which direction is V cross B?
I always forget which one is into the board and which one is out of the board.
So this is the back end of an arrow. The front end of an arrow is this, the tip.
See, I've never heard of that.
And, you know, you have the feather part, right? Yeah.
So it's up, right?
It's upward. Yeah. So you get an F magnetic. So this EMF is going to be created by that. Okay. Now, mind you, over here you get the same thing. It doesn't create any current. And over here, V cross B is still which way? Still this way, right? But if charges are moving this way, the charges want to, well, regardless, if there is a velocity in this direction, it is somewhere in this direction, but the magnetic force here does not lead to any current.
It's only because it's not against the...
Right, it's not along. Yeah, charges simply cannot move. So we won't worry about this part. So I want to draw a couple of diagrams. One is the charges. So you have, and I'm going to make it bigger, V. And because of the magnetic force, it's going to suffer some amount of U. Okay, so this would be U. I don't necessarily want to draw a 45-degree triangle. Sorry. Because it's misleading when I draw a 45-degree triangle. It could be any angle. You know, we don't know how much.
What is U?
Oh, because of, good question, because of the magnetic force, the charges are now going to start moving vertically up along the wire. Yeah? So it's going to create some velocity in the direction along the wire.
So it's a velocity term.
It's a velocity, yeah. And it has to be because I'm drawing this in the same diagram. And I get a net velocity here. But let me also bring this over here so we can get some angles. So this is U, and Griffiths decides to call this angle theta instead of this angle. That's fine. As a result, now I have to be careful. I have to draw a similar diagram. And I'm going to make it this long. The length of this wire. But the charges are actually moving a simple problem. I complicated it by drawing two similar triangles. One is along with the velocity axis, U and W. As a result, charges, see, the charges are moving up here, it's moving this way, so as the frame moves, these charges are moving in an angle. So that's what I mean here. This is a vector L. Yeah? And this H is simply okay, let's do some physics. What is the EMF generated in the loop? That is F mag dot dl, and force per unit charge, VB. Is that clear that it's VBH? Yeah? At one instant of time, you take a photograph, and at that instant, I'm doing, the closed integral. but only in this part will it contribute. So you're getting an EMF in the circuit. And now, if there's an EMF in the circuit, I mean, there's a current in the circuit, resistors get heated up. Who's doing the work? Well, we know who's not doing the work. It's not the magnetic field. Obviously, in this case, who's doing the work? The other guy. So let's connect that. Okay? Now, because of this motion, the charges feel a new magnetic force, like an extra magnetic force. Right? It's in the V cross B direction, or I should say, it's in the U cross B direction. So what is the new force that is created? Which way does it point? Do U cross B. I'm going to draw it. I mean, it's going to be here, but I'm going to draw it here because that's the origin. Which way is going to be what's the direction? Yeah, good. That is exactly right. Right? To counteract this, oh, by the way, now if I draw the net, at any point, if I draw the net magnetic force, I would get, first draw the answer. And now that I know the answer, I'm going to get this over here, and from this guy, I'm going to get this over here, so that the net magnetic force is actually perpendicular to the direction of the motion, and there is no work done by the magnetic field, because we know magnetic fields simply do not do any work. Yeah? So that's how the magnetic field is not doing any work. But because of this guy, this object is hard to pull. So the person pulling will have to do what? They'll have to, for lack of a better term, I'll call it F pull. So let's calculate the work done by F pull. What's the, let me write F pull down. It is U cross B, the direction is UB, let's say in the X hat direction. Correct? So then the work done, and we know what the answer should be. What should the answer be? That. So the work done by this person, we don't have to really do any integral. F pull dot dl. Everything is uniform. It is F pull. That's why I wrote this vector L. The charges are moving from here to here. So that is going to be equal to F pull, you know, is UB. Now, this answer is in H. And this, well, UB L. I have to convert U to L to H using just trigonometry. So what is, let's look at this triangle. What is it? Cosine theta? Cosine theta is H over L. not UBL, it is F dot L. F times L times cosine of what?
The
Angle, but this is a weird angle. This is the angle that's given to you. This is F po. So what's the angle? 90 minus 10. That is UBL sine theta, and that's equal to UB sine theta. L is H over cosine theta. H over cosine theta. That is UBH tangent theta. Then I'm going to look at this triangle. So I'm going to draw it one more time. V U this is theta. So what does that mean? This is theta, correct? And we need tangent theta. What is tangent? Opposite over adjacent. So that is U B H V over U. It's very convenient because I know the answer. That's exactly how I remember that I've dropped off the cosine bit. And lo and behold, the magnetic field did not do any work. The person pulling did work. Lots of detail here.
So a clarification, despite the person pulling in the exact direction, right?
Yeah.
The work comes from the path interval, and because he's pulling effectively at this, that's why the DL becomes the path of the L.
Correct, because the charges are moving in this direction. Yeah.
So the initial pull is what changes it, right?
The initial pull is, yeah, we're assuming it reached a steady state. That's a good question. So this loop is a long loop. So, you pull it for a couple of seconds. It doesn't take long to get steady state. You pull it for a couple of seconds, and you have, they have figured it out. If you pull exactly with a speed, certain speed V, it reaches steady state, right? It depends on the magnetic field. Yeah? And no, for every speed V, there's a corresponding U. And they figure it out so that it just balances off. And then it's steady state, but the loop is still long, so you can still conduct the experiment. Yeah. That is a good point. We have reached that steady state before we did the calculation. But there is a nice way to get VBH. But it turns out that nice way is very general and not specific to this problem. So first, let me make it clear what is it that I'm talking about. So the magnetic flux through the loop phi is given by, well, that's easy. It's B dot, well, let me recall what is magnetic flux. It's B dot dA. We won't be doing any calculus for this, it's just B times A. In our case, it is B, H, and then there's only flux through this much, right? So let me call this distance X. And then let me do the rate of change of magnetic flux. Well, that's easy enough. It is BH dx dt. Now, you want to say dx dt is V. But why the negative sign? Look, the more you pull, x is decreasing. So dx dt is a negative number. The number v, the magnitude we have given, is a positive number. So it's that. And so you get a simple coincidence that says the EMF is the negative change of the magnetic flux. Yeah? But this is the most general result. In a complicated way, if the shape is not a perfect rectangle, even worse, the shape is expanding and doing whatever it does, this is the most general result. So that's a theorem, and I'll give you proof. The theorem itself, I'm not going to write it as a theorem. This is always true, even if what? The shape of the circuit changes.